Anyway, I'm Yamamoto from the University of Tokyo. Still, I will continue to be the chair for the next two presentations. And it's my great pleasure to introduce the first speaker, Professor Oleg Imanimilov from Colorado State University. And as you as you know well, he created very fundamental Karem estimate with the singular weight functions, uh, which are essential for exact controllability for parabolic equations. And after that, he has achieved many works for control theory and also inverse problems. Today, he will give a talk entitled by Remark on Controllability to Trajectories of a Simplified Fluid Structure Interaction Model. Oleg, could you please start?
Yes, Masahiro. So first of all, I would like to thank the organizers for possibility to give a talk. Today, I'm going to talk on two problems. One problem is remark on controllability to trajectories of a simplified fluid structure interaction model, and another is on the chain of Schrodinger equations. Okay, mathematically, actually, the two those problems they are more or less the same, and include the chain of parabolic or Schrodinger equations connected via some boundary conditions. So let me formulate the first problem. Okay, we consider the segment. Omega is segment AB. A and B are numbers, and 0 belongs to this segment. When we consider cylinder Q, 0 capital omega. Well, we consider a couple of semi-linear parabolic equations. So we divide domain cylinder Q in two cylinders. Q plus is 0t capital times segment 0b, and Q minus is 0t capital times segment A0. Well, function W1 of x is defined on the cylinder Q plus and satisfies to the semi-linear parabolic equation. So it's this operator I denote as a G1 of x W1. So variable x is x naught and x1, where x naught is a little bit unusual, is a time variable, and x1 is space variable. And the reason for such strange notation for the time variable I use x naught is because later I use a lot of pseudo-differential operators, and if I keep notation t for time, formulas would be way too long. Anyway, operator G1 of xw is a standard semi-linear parabolic equation, non-linear term G1 depends on W1 and its derivative. Well, once we work on it, we kept in mind for example, Burger's non-linearity. Well, and in the cylinder Q minus, we have function W2, which satisfies a similar semi-linear parabolic equation, with non-linear term G2, well, and some other coefficients rho A, B, C2. Okay, how are those two functions connected? The functions connected via the boundary condition at the moment x equals 0. We have W1 equals W2, and derivative respect to space variable x1 of w1 minus derivative respect to x1 of w2 minus some fixed positive constant m times time derivative of the function w1 at the moment moment x naught and x1 equals 0 equals to some function r of x naught. Everything is equal to 0. So here r is given smooth function and m is strictly positive constant. Besides of this condition, we have two Dirichlet boundary conditions. So w of x naught b and w2 of x naught a were equal to 0. Also, we have the initial condition prescribed. So w of at the moment t equals 0 equals to the given function w naught. Okay, sometimes actually so for us would be convenient to introduce the function w of x, which is equals w1 for x in the cylinder q plus and w2 for x in the cylinder q minus. Well, if you return back to the slide 2, in the right-hand side of each semilinear parabolic equation, we have given functions f1 and f2 and control u, which is locally distributed in domain omega. So its domain omega is an arbitrary small subdomain of the segment 0b. So we have control only in the first equation. Yeah, result would be the same if I'll instead of placing control in the first equation, I'll place control into the second equation. Say it would be f2 plus characteristic function of omega times u, and here we will have 0. Well, we'll consider the standard controllability problem. So we have a target function w sub t of x1 is given, and we need to find a locally distributed control u such that at the moment t capital w of t equals w sub t. So that's a standard control problem. But we actually should explain the difficulty. So most difficulty here comes from the boundary condition at the space moment x equals 0. When two functions w1 and w2 are iterated, and the difficulty is caused by this term, time derivative of the function w1. That's caused the most of the technical difficulty. Okay, now let me formulate the result, and I'll try to explain a little bit the technique. Because coefficients of the semilinear parabolic equations, ρ1, a1, they satisfy the following regularity. It's C1 functions in time and space. B1 and B2 are from L infinity. C1, C2 are from L infinity L2. And space derivatives of B1 and B2 were also from L infinity L2. So next, the standard positivity condition. ρ1 of x is strictly positive on the cylinder Q plus. A1 of x is strictly positive on the cylinder Q plus. Same for row 2 and A2. The semi-linear terms, G1 and G2, C2 in all variables, all three variables. Yeah, and of course, they satisfy some additional growth assumptions. For example, GK in Xi1 and Xi2, they grow in Xi1 at most as Xi1 in the power P1, and in Xi2, which corresponds to the gradient, as Xi1 in the power P1 times absolute value of Xi2. Once again, this corresponds to the nonlinear term of the Burger's equation. Well, the same, of course, yeah, it's same for both semi-linear terms. Then derivatives, when we differentiate in respect to Xi1, functions gk, such function is grow as much as Xi1 is the power P1 minus 1 times Xi1 is the power P1 P2 minus 1 times absolute value of Xi2. Well, also we assume some growth on derivatives in Xi2 and its mixed partial derivatives. Okay, its grows no faster than Xi1 in the power P3, and once again, actually, all those conditions they satisfy to the nonlinearity of the Burger's equation. Well, since we are dealing with parabolic equations, it is well known that we cannot reach an arbitrary target function W sub t. So we need to introduce some special condition on the target function. Basically, the target function is supposed to be on the trajectory. So we assume that there exists a function W, which satisfies to our semi-linear parabolic equations G1 of xw1 and G2 of xw2 with U here is some control distributed in the cylinder Q omega. Yeah, but the initial condition is not specified. So this function W satisfies to the boundary, same boundary conditions. Yeah, and at the moment T capital, W of T capital equals W sub T. Well, we don't know the value of double function W at 0. Yeah, but that seems to be the standard assumption on the target function. Okay, then the result is following. Existence theorem. So if functions right hand side f1 belongs to L2 Q plus and f2 belongs to L2 of Q minus, R belongs to L2 0 T capital. Yeah, and suppose that functions f1, f2, R and W sub t, they satisfy to this condition 1, which was just formulated. The initial condition W naught is from H1 naught omega, and it is sufficiently close. W naught is close to W bold of at the moment t equals 0. So as I already emphasized the fact that in condition 1, we don't have any assumptions on the value of function w at the moment t equals 0. Yeah, but that condition means that we staying close to the trajectory. Okay, then our controllability problem has solution pair w and u. U is control. So it's w has a following regularity h1 to h1 in time, h2 in space, continuous function in space h1 not omega, and the locally distributed control u is from L to Q. Well, and support of the function u belongs to the domain Q omega. So that's the main existence result for this problem. And if I go back, it helps very much that the two equations under the consideration are parabolic equations. So it's later I'll consider the case of the Schrodinger equation. We can consider, of course, more or less a similar problem for Schrodinger equation, beam equation, or chain of the wave equations. And what happens in all those three cases, if you not consider the parabolic equation, but beam, Schrodinger, or wave equation, well, you are starting in observability inequality, you're starting to lose regularity. So in the case of parabolic equation, loss of regularity would not happen. Well, it's some technical problems when you're doing the observability estimate by the Karleman estimate. You are just losing power of S, and the weights are deteriorating, but regularity stays. So that allows me to consider also the semi-linear terms here. Let me give the quick history of the problem. Well, kind of many works are known, so it's me refer just several of them. For example, Anna Dubova and Fernandez Carre. So it's, they also established the controllability to trajectories for this problem in 2005. Well, the restriction was the trajectory. It was the equilibrium solution. Well, some efforts have been done when equations are involved in the model are just linear parabolic equations. For example, works of Scott Hansen and Martinez, and works Tunisian mathematicians Ben Amara Bouzi. Well, in the case of the chain of parabolic equations with time-independent coefficients, they proved the corresponding global controllability to the trajectories. In the linear case, which would mean that if equation is linear and condition 1 holds true, that assumption of that your initial condition W naught is close to the trajectory W at the moment t equals 0. Yes, is absent. But that's a common situation in the case of controllability of the linear parabolic equations. Okay, and the next. Yeah, of course, our technique also allows to consider the chain of linear parabolic equations connected on the interaction point by those very similar boundary conditions. So let me now consider the chain of Schrodinger equations. Well, we're in a similar situation. We have one-dimensional domain omega, which is open interval, left interval d naught, and the right end of the interval dn plus 1. And this interval is divided in sub-interval by points dk. So it's omega k is dk minus 1 dk, and yeah, of course, dk is strictly less than dk plus 1. Well, the cylinder qk is 0 t capital times open interval dk minus 1 dk, which we denote as omega k. Yeah, we consider vector function w, which is w1, wn capital plus 1, and f capital would be vector function f1, f capital n plus 1. Well, we consider the following control problem. So on this each cylinder qk, yep, we consider one-dimensional Schrodinger equation I rho k dx not wk minus ak second derivative of wk plus first and zero order terms equals to given fk, and plus the control, locally distributed control in domain omega. Control will be localized, and control will be only in the cylinder. Omega will be only in the cylinder dk plus 1. Yeah, so if you drop square root of minus 1, you drop I, you get the similar problem I mentioned for the linear parabolic equations. So functions wk and wk plus 1 were connected at the point dk by the boundary conditions. Wk at x naught dk equals wk plus 1 of x naught dk. And another condition, yep, which is pretty similar to one I consider in the case of parabolic equations, I times ak derivative respect to x1 of wk plus 1 minus ak derivative of wk respect to x1 minus mk time derivative of wk at point dk equals to some function rk. So it's r is given smooth function and mk are given positive constants. Okay. At the left and the right endpoints of the cylinder, we have just Dirichlet boundary conditions. W of x naught d naught equals W of n plus 1 x naught dn plus 1, it's equals 0. Yeah, of course, we have the initial condition, say W of 0 equals V naught. When we have a locally distributed control, it's locally distributed in the domain omega, and control just placed is the segment dn plus 1. So it's omega is d up to dn plus 1, where d belongs to dn plus 1. So if we return back, here, the locally distributed control appears only in equation for W n capital plus 1. In all our equations, we have, in all our n equations, we just have the fixed right-hand side. Yeah, we're making the standard assumptions. Assume that all coefficients are C infinity functions, and rho k and a k were strictly positive. So under those assumptions, we are indeed dealing with the Schrodinger equation. And such a strong assumption on the regularity to the case of the parabolic equation. Well, the reason is the following. As I mentioned, we are very unfortunately, actually, I'm kind of losing the regularity when I'm trying to prove the observability inequality. So it's how proof goes. So we start observability inequality for the function W n plus 1. So we have one observability estimate for this function with one regularity for the next function Wn. We basically so losing the one derivative in space and half derivative in time. So that would be the reason why I require such high regularity from the coefficients of the Schrodinger equation. So and the main theorem will be the following. Say I would like to try to find the control, locally distributed control U, such that at a precise moment of time t capital, I would like to transfer the initial condition into 0. Yeah, that can be done provided that functions f1, fn were from L2, r is from L2. The initial condition, sorry, should be v naught, is from c infinity naught omega k. So it's basically, so its initial condition is is equal to 0 in the neighborhood of each point dk. And in order to have compatibility conditions, I'll assume that functions f1, f2, fn plus 1, and r were all equals to 0 near t equals 0 on some open interval. Okay, then the controllability problem has a solution C from 0 t capital L2 omega h1 naught. Yeah, so it's in that case, of course, because we're dealing with a linear equation, there's some no restrictions and nothing like the condition 1 as I used in the case of a chain of equations in the parabolic case. Well, there are also some results, of course, for this problem. So most close one is by Avdonin and Edward, where they proved the similar result, solving the moment problem in the case when coefficients of the Schrodinger equation were all time independent. Yeah, and well, the Schrodinger equation, of course, is connected to the Bernoulli equation, Well, it's a similar result by the moment problem technique was obtained by Mercier and Regnier for the chain of Euler beam equations, basically Euler-Bernoulli beam equations. They are connected via similar conditions. Okay, but of course, because in X this equation is of order 4, where a little bit more bound conditions at the point of interactions. So now I still have a few minutes. Let me talk about the technique, for solving the problem. So technique includes, I'll talk about the problem of parabolic equation. So technique includes the Kahneman-based Kahneman estimates. But the special, essentially, is a very special function. So one function, phi1, we use for the cylinder Q plus, and in our function phi2 we use for the cylinder Q minus. Okay, function phi1 is greater than phi2 on the Q plus, and the function phi2 is greater than phi1 on the Q minus. So we first actually constructed phi1 and phi2 in whole Q, and then we use phi1 in the cylinder Q plus and phi2 in the cylinder Q minus.
Oleg, you can have about 5 minutes.
Yes, yeah. In that way, actually, so we have the function phi star. So those functions for x equals 0, function phi star is continuous, but derivatives left and the right space derivative are discontinuous. Okay. Then we introduce the space y. So for the function, any function f which is defined in the cylinder Q, so it's so norm is given square of norm squared of L2 norm in Q minus, and weighted L2 norm in the Q plus. So it's in Q plus norm is stronger. Also introduce the space X, space of the functions. So U belongs to H1 to Q plus Q minus. So it's U is continuous for X equals 0, and U of 0 belongs to H1 0 T capital. So and when X equals A or X equals B, U is just equals 0 for all T. So that's not the standard Sobolev space. So next we introduce operator P, which includes a parabolic operator. So K is parabolic operator rho U sub x naught minus U sub x1 x. And so operator actually of condition on the interaction as when x equals 0. This operator will map x into y times L to 0 T capital. Then we introduce operator B, which for each function v includes right and left partial derivatives at the moment x equals 0, and weighted space z. There is space of functions defined on time interval 0 T capital, with different weights. Okay, then we have the following observability estimate. So it's if U belongs to X, okay, where is this two constant S0 and C1, such that the following observability estimate holds true. So it's right-hand side here. This term is essentially corresponds to the value of operator P on U. So this is our weight function y phi star, which is degenerate at the moment t equals 0 and t equals t capital. And so here is observability data, which is normal derivative of U at X equals P. So that's the observability estimate. And if you look at the weights, here the weights in the domain Q plus are much better than weights in the domain Q minus. Okay, the similar estimate is holds for the Schrodinger equations, but in that case, as I mentioned, for the Schrodinger equation, we are losing the regularity. Okay, so I guess I'll stop here.
Okay, thank you very much, Professor Ivanilov. Okay, now the time is open for discussions and questions and comments. Do you have any questions or comments? Now the time is open for that. Okay, somebody. Okay. Mm-hmm. Okay, just I have one question. I think there is quite a strong physical background for one-dimensional case, but the multi-dimensional case, one needs not consider at all. Or
no, it was considered.
Yeah.
Yes, so it's even situation might be more interesting because different geometries. So it's in case of linear parabolic equation, the multi-dimensional case was considered in the works of let's see, Robiano, and we might see actually, so it's there are possibilities with geometries, how domains are located. Say you have a domain constructed with cylinder Q plus and Q minus in the following way. You have just take an arbitrary domain. Yeah, you might cut off some domain, denote it omega plus subdomain, and what left outside of this subdomain omega minus. And the situation actually so depends. We consider parabolic equations with time-independent coefficients. So essentially, we've been dealing with elliptic problem. Yeah, but because of multi-dimensional case, it's situation actually so depends where you put the control in domain which is inside, and always domain place control on domain which is outside. So results are different. So here in one-dimensional case, actually, so that doesn't matter.
Yeah. Okay.
Yeah, so it's, I can place control on the segment 0B, and I can place control on the segment A0. So it's, that doesn't matter, but in multi-dimensional case, situation is different.
Okay, then I can understand that the not yet completed, especially the multi-dimensional case.
Yeah, no, it's completely the case actually. So time-independent coefficients.
Time zone. Okay.
And of course, linear equations, parabolic equations with time-independent coefficients.
Okay.
And
Okay.
the Schrodinger case, the non-linearity here. If you put here, say, the semi-linear term, so it depends just on WK. The non-linearity is a real problem. I don't know how to deal with it. So it's Enrique and Scott Hansen been dealing with that, guess in the case of, if I'm not mistaken, Enrique, in the case of one-dimensional wave equations.
Okay. Okay, thank you very much. Do you have any questions or comments? Is it okay?
Okay, is it okay for me to stop share?
Yeah, then once again, thank you very much, Professor Imanibirov. Yeah, then could you please stop the sharing the screen? Yeah, thank you so much. Thank you so much. Then I think immediately we should go to the second presentation. The next speaker is Dr. Hiroshi Takase from the University of Tokyo. This framework is how to say for the younger, and the short presentation, short means that 25 minutes, and he will give a talk entitled by inverse problems for first order hyperbolic equations. Okay, Dr. Takase, could you please start?
Okay, thank you very much for your kind attention. And first of all, I would like to thank all organizers to giving this opportunity to talk in this wonderful workshop. And okay, this is a joint work with one of the organizer and my friend Giuseppe Floridia. Okay. Oh. Okay. So, okay, this talk consists of 3 sections. And I would like to explain 2 kinds of inverse problems. The one is inverse source, and the other one is inverse coefficient problem. And I talk about each problem after introducing some mathematical settings. Okay, this is a constraint equation. The hyperbolic operator P consists of A0 partial T plus the vector varied function A dot nabla. We consider this hyperbolic equation in the cylindrical domain Q, where Q is defined by omega times 0 to capital T. Here, omega is a bounded domain with ellipsis boundary. And let me define the sub-boundary of the cylindrical domain. So sigma plus denotes the outgoing boundary, where the inner product of the vector varied function A and the outer unit normal nu is positive. Okay, we call this sub-boundary outgoing boundary. And as the complement of the outgoing boundary, we define the incoming boundary. So let me explain briefly using by this simple picture. And this is these lines are integral curve or characteristic curve of the vector varied function A. And the red part denotes the outgoing boundary. And of course, the complement is incoming boundary. So actually, I should have written this picture in cylindrical domain because the coefficient A depends both space and time. So, but for simplicity, I wrote the picture as a projection to spatial, how to say, the base of the cylindrical domain. And today we consider this inverse problem. Can we determine unknown functions, namely source f and the coefficient A0 and the vector varied function A by observation of the solution U on this outgoing boundary? This is the inverse problem today we consider. Okay, more mathematical settings. Okay, the first one is the inverse source problem. In this inverse source problem, this source time is unknown. And given the potential P, which depends on the both time, space and time, and boundary data and initial data, we discussed the uniqueness and stability to determine the source sum F from boundary observation on outgoing subboundary. And okay, the second problem is inverse coefficient problem. In this problem, the operator P is unknown. Okay, so more precisely, the coefficient A0 and the vector valued function A are unknown functions. And we discuss the uniqueness and stability to construct A0, A1, blah, 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 AD. So I don't mention it explicitly, but A1, blah, 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 AD are the components of the vector valued function A. Okay, so we discussed the uniqueness and stability to construct this D+1 unknown functions from D+1 observation data. Okay, so first, I would like to show what we want to prove in this talk. The first problem, in inverse source problem, there are few hopes to guarantee general f of xt. So we usually assume the source term f of xt has a multiplication form like r of xt times f of x, and we assume this r is known and this f of x is unknown term. And what we want to prove is a so-called global ellipsis stability, namely the sum norm of the difference of f1 and f2, which are unknown functions, are bounded by the observation data on outgoing subboundary. So, okay, because this inverse source problem is linear problem in a sense, so it suffices to obtain the sum norm of f is bounded by u. Bounded by constant c times observation data on outgoing boundary, u. So, okay, here u solves, of course, homogeneous initial and boundary value problem. And the second one, inverse coefficient problem, we assume the coefficient A0 and the vector valued function A are not depend on, do not depend on time t. So just space variable. And what we want to prove is the global ellipsis stability as well, namely the summation of each component. The summation of the difference of each component is bounded by constant c times the D+1 observation data on outgoing subboundary. Okay, this is our goal. So there are some cases to prove Helder type stability if one observes observation data on a part of subboundary sigma plus. But in this talk, we focus on just global stability, namely these two estimates. Okay. So I briefly mentioned the previous works. In 2014, they proved ellipsis stability with time-independent coefficient. And 2006, this is 2014, and this is in 2016, they proved the ellipsis and the Helder stability under the assumption that suitable weight function exists. And 2019, they proved the Helder type stability in a wider class of the coefficient A than that of 2, but not ellipses. In this talk, I showed the results, namely ellipsis stability with time-independent coefficient. Of course, we can get the local Helder type, but we focus on the ellipsis in this talk. Okay, now let's go to the details of each problems. Okay, and the first one is inverse source problem. this is our constraining equations. And this is one first order hyperbolic operator, and this is potential term. And we assume the source term f is separated by r of xt time f of x. And okay, to obtain the main result, we assume three assumptions. The first one is the positivity of the coefficient a0 and the norm of a of xt. This quantity, we assume this quantity is strictly positive in the closure of cylindrical domain. And the second one is dissipativeness. So, sorry, I haven't explained the definition of dissipativeness, which is explained in the next slide. But this is one of the assumptions. And the third one is, the third assumption is, how to say, so roughly speaking, the partial t, regarding on the t derivative of the vector valued function a. Roughly speaking, partial ta is bounded by a itself. This is a rather strong assumption. So yeah, of course, I explained the third assumption later. And okay, under these assumptions, for sufficiently large capital T, there exists constant C, which is of course independent of F and U, such that this Lipschitz stability holds, which is proved by the Bufgame-Kuribanov method. Okay, in the next slide, I show the definition of dissipativeness of the vector valued function A. So, okay, before defining the dissipativeness, we reviewed the definition of integral curve and maximalness. The first one is integral curve. A curve C sub x is called an integral curve of the vector valued function x through small x if Cx satisfies this very simple first order ordinary differential equation in short time interval sigma. And furthermore, a curve C defined on a closed time interval is called maximal if it cannot be extended to any slightly large segment comparing to the original one. Okay, this is a maximalness. And combining these two assumptions, we define the dissipativeness of the vector valued function x. Namely, vector valued function x is called dissipative if for each x, the maximal integral curve Cx is defined on a finite segment, and furthermore, this function is continuous up to the boundary and has enough regularity. For example, 82 class. Okay, so let me explain using this picture. If vector valued the function x is dissipative, for each x, the integral curve exists in a small time interval. And the dissipativeness requires this curve extended to the boundary and define the endpoint, how to say, endpoint time function sigma minus of x and sigma plus x. And moreover, dissipativeness requires this endpoint function sigma minus of x is continuous up to the boundary and H2 class. So, okay, let me show some very simple example in two-dimensional space. This is a very simple example. Let B sub R be an open ball with radius R centered at 0. And the first example is minus x minus 1 in upper ball. So in this case, the maximal integral curve is calculated by solving the initial problem of the first order differential equation. First order differential equation, and we can prove x is dissipative by using, for example, implicit function theorem. Moreover, the function sigma minus which is the endpoint time function, is smooth up to the boundary. And the second example is rotating vector field case. We consider this rotating vector field in the annulus domain. So in this case, because the integral curve has this form by calculated by solving the initial problem of differential equations, the integral curve, it can be extended to minus infinity to infinity. So this is not finite. So X is not dissipative. And in this talk, we assume that this first case, dissipative case. Okay, under this assumption, namely the positivity and dissipativeness of the initial vector valued function, we can prove the global Kalman estimates, which is an important tool to prove the inverse problems. And due to this dissipativeness, we can define the length of the integral curve. This is length phi 0 over x. This is nothing but the length, the definition of the length of the integral curve. And okay, the phi 0 x means the length from the boundary to x. This is a length. And using this length, we define the weight function phi of xt as phi 0, this is length, minus beta t, where beta is positive constant. And okay, by choosing this weight function, we prove the so-called global global Kalman estimate. There exists constant C such that for sufficiently large S and U, which is in H1 class, this a priori estimate holds. Okay, in the next slide, I showed the outline of the proof of this estimate, just one page. Okay. I explained the proof, just second step, just two steps. The first step is set new function z using the large parameter s and weight function phi constructed just before, and okay, set new operator ps as follows, and making a lower bound of L2 in a product of PSC. Okay, I omit this process, but this is done by using just integration by parts. And also I omit the details of the calculations, but I think there is just one essential point of the proof, which is the positivity of P phi. Of course, P is our first order hyperbolic operator, and phi defined by this is the length of the integral curve and minus beta t. Yeah, this phi is the weight function constructed before. And okay, yeah, at this point suddenly we assume A has the representation. Sorry, suddenly we assume that, but please wait doing a question. Suddenly we assume that there exists capital phi such that A of xt can be written by this scalar function times the initial vector field. Then the positivity follows from by using this representation formula, the positivity of P phi follows as these calculations. So, okay, let me explain it. P phi, because very simple. The P phi is, P phi is by definition corresponds to this quantity. So because we define the weight function, this one, and by using the representation formula to A of xt, so because A of xt is written as scalar function and initial vector valued function, this is trivial. And by definition of the length, this quantity A times the number of lengths is the norm of initial vector valued function. And next, by using the representation formula again, this quantity is nothing but the the norm of x over t. And okay, because we assume the positivity of a of xt from below low, then if we choose beta sufficiently small, this quantity is positive, and we can prove the positivity. So, okay, let me say just one remark. The representation formula, SPADE, is too strong assumption. Of course, too strong, just to obtain the Kahneman estimate. However, this representation assumption certainly simplifies the proof, as you can see. This is very simple proof. Just one remark. Okay, so let's go to the main result again. We assumed three assumptions: the positivity of the coefficient and the dissipativeness of initial vector valued function, which is already explained. And the third assumption is regarding the time derivative of the vector valued function A. Okay, under these three assumptions, we get the Lipschitz stability. So, okay, in the next slide, we explain the third assumption. What is the third assumption? The third assumption, the red one, is mainly used to obtain the energy estimate. So energy estimate means the quantity E of t defined by this quantity associated to the considering hyperbolic operator is less than or bounded by constant c times f. This is unknown source, which will be used to prove the main result, whose proof is omitted in this talk. Okay, this third assumption is mainly used to obtain energy estimate, not Kahneman estimate. But this assumption, the third assumption, implies the representation formula of A, which simplifies the proof of the Kahneman estimate. More precisely, which simplifies the proof of the positivity of P phi. Okay, its proof is very simple, so let me explain. When D is greater than 2, because D equal one-dimensional case is obvious, so when the dimension D is greater than 2, there exists a perp, which is also gonal to A. And by using this third assumption, by instituting the Xi to a perp, the right-hand side is 0. So the left-hand side is 0, of course. So which means partial TA is proportional to A. And by solving the first order ordinary differential equation, setting capital phi means this representation formula. Okay, so what I want to say is that the third assumption is important not only to obtain the energy estimate, but also obtain the representation formula, which simplifies the proof of the Kahneman estimate. Okay, so let me explain the outline of the proof of the main result by Bufgame-Krivanov method. So for simplicity, we denote norm sub Q means the norm of L2 norm. Okay, and okay. Before describing this method, each step is mathematically not rigorous, but because this method is very complicated and difficult to present in a talk. So at the sacrifice of the mathematical correctness, I try to explain the method just 4 steps. The first step is applying the Kahneman estimate to the t derivative of u, and one can obtain this estimate. And the second step is making an upper bound of this first estimate by using the energy estimate. This is the right-hand side. This quantity corresponds to the right-hand side. And the third step is making the lower bound of the left-hand side of the first step. Namely, this is very trivial estimate. And combining 1, 2, 3 estimates, this quantity is bounded by this quantity, and this quantity is bounded by this right-hand side, and this quantity bounded by this one. So finally, we obtain this one, and by choosing S large enough, the first term is absorbed in the left-hand side. So we can make the upper bound of the unknown source term F. So this is the outline of the Wolfram-Kribanov method. Okay, maybe almost 1 or 2 minutes. Let me explain the inverse coefficient problem. So this is a constraint inverse coefficient problem. We discussed the uniqueness and stability to determine A, the coefficient A0, and the vector valid function A from D+1 observation data on outgoing boundary. Okay, now this is the main result for inverse coefficient problem. So, namely, after setting appropriate conditional subset of this functional space, sorry, I omit the details. So, okay, this is the main theorem. For sufficiently large capital T, we assume the positivity of the known functions P of x0 and determinant of the matrix constructed by initial data. So we assume this quantity is uniformly positive. Then there exists constant C, which is of course independent of the unknown coefficients, which are in the conditional subset defined before. We can obtain the Lipschitz stability, Lipschitz type stability. Okay. So this positivity condition requires us to choose different D+1 different observation data. Okay, and now let me. Just 1 or 2 minutes. So we see inverse coefficient problem comes down to inverse source problem by just subtracing 2 equations. In the first step, this is not first step because I just write down the equations which UI solves. And the second step is defining the difference of the U1 and U2 and the unknown coefficients, and this is remaining term, and just subtracing, we get this equation. So surprisingly, or maybe not surprisingly for some people, the difference of the unknown coefficients moves to the source term. And the third step is considering the inverse source problem to determine F, which is done by the Wolfram-Kribanov method. Okay, this is the outline. And let me explain just one remark. When is the positivity assumption used? In the last step, one must make a lower bound of this type. Here, the red part F is unknown source term. So sorry, unknown coefficient, and the difference of the unknown coefficients. And R of x0 has this form. And in this step, one uses a positivity assumption, namely determinant of R of x0 is greater than positive constant, which means R has bounded inverse. So this lower bound holds. Okay, just one remark. At the last slide summary, we introduced the dissipativeness for vector fields and proved global Lipschitz stabilities for two inverse problems. And the dissipativeness is important to establish the global karma estimate. And the third assumption, regarding on the time derivative assumption, is mainly used to obtain the energy estimate, which is used to prove the main results. But moreover, this assumption implies a representation formula of the vector value function A. And the formula simplifies the proof of the global karma estimate. Okay, that's all. Thank you very much for your kind attention.
Okay, thank you very much. And unfortunately, the time is pressing, and maybe one short question or comment. Do you have some question by chat? Okay. There's one question.
Manifold.
Yeah. Okay,
I can see the question. Okay, so yeah, it's possible to extend this result in a Riemann manifold, but the equation is first order. So I think any geometrical invariance, for example, sectional curvatures and the other, scalar curvatures, do not appear. So yeah, do not appear.
Yeah, but to such question, one can interpret not necessarily plane domain like a curve or the surface.
Yeah, definitely. So yeah, of course we can extend to the Riemann
like
manifold.
Surface flow on the Earth or something like that.
Yeah, just considering the integral curve, so we can easily extend.
Is it okay? Okay. Then now the time is over, and thank you very much. And once again, I would like to thank all the speakers, including before the lunchtime. Sorry, I misunderstood. But anyway, all the speakers in this session, I would like to thank excellent talks, and also I would like to thank the audience for inspiring the session very much. And thank you very much. Now I would like to close this session. Then I will change to Giuseppe.
Okay. Thank you. First of all, Professor Yamamoto, as chair of this two slots, very precise chair. Thank you. Thank you also, Professor Emanuilo, to have accepted to give a talk in our INdAM workshop. We are honored about it. And then we start again 4:40 with the Domenech Ruiz Ballet, and after the last conference by Professor Gunder